Okay, thanks everyone. It's great to be back in Santa Cruz. It's been about 4 years since I've been here, and it's really good to be back at Joel Fest. So Mike gave a great introduction to the work that I'm going to be talking about. So this is work done with Mike and the CANDELS team, also with Ella Reza and Greg Schneider, who are both here this week. So just so I give you the summary before I go on too long and maybe I don't get to the end here. As Mike was saying, galaxy morphology can trace underlying physics of galaxy evolution. I'm going to show you some pretty pictures from the frontier fields that kind of demonstrate that. But sometimes if you really want to understand, use morphology to its full extent, you want to capture sometimes rare events and often subtle features. And I would argue that putting things in a sort of a traditional Hubble sequence or using a Sirsic index to classify something as a disk, spheroid, or something else doesn't really use the full amount of information that we have from Hubble images, even at high redshifts. So as Mike presented, we've developed this Pca Analysis of these 7 non-parametric morphology measures and looked at galaxies above redshift 1 and at high masses. And I'll argue that this approach is actually finding objects that are the structural progenitors of today's large early type galaxies. Those things are rare. They tend to be star-forming and massive at redshifts 2. And their frequency is increasing rapidly after redshift 1.5. But they seem to rise before the disappearance of the massive compact galaxies. And so the origin of these objects is consistent with multiple formation pathways, possibly including the growth or regrowth of disks around compact galaxies and then subsequent quenching of those disks, much in line of what Marcella was talking about this morning. So I thought I would take a minute and advertise the work that I've been doing other than morphology, which has been leading the frontier fields. This is our pretty press release image of Abel 2744. But it doesn't really do justice to the full depth of these images. If I now go to the WISC3 IR and zoom in a bit, you can see what I'm talking about in terms of looking for sort of rare and subtle features to give you a sense of what the physics is going on with these galaxies. So this whole program is largely designed to look for highly lensed galaxies behind the cluster, but we're learning a lot of cool stuff about the galaxies in this redshift 0.4 cluster. So if I now move from the IR to an optical band and zoom out a little bit more, and then focus in on a couple of really interesting objects on the edge of this cluster, we can see ram pressure stripping in these beautiful spiral galaxies. We call these kind of jellyfish galaxies, these faint blue trails coming off. And if I look in this upper corner, oops, go back again here. Yeah, we have these spirals here. There's dust lane here. We call this the coffee stain. But then there's this really interesting object here, which is, an early type galaxy that looks very much like it's losing its gas and it's being ram pressure stripped as well. So just highlight, this is not something that's captured with a Sirsic index in any sense. So as I said, one of our goals often in astronomy and in fact for James Webb is to look for the evolution of the Hubble sequence. But I think perhaps the Hubble sequence is coming to the end of its usefulness. Roger Davies would argue that the Hubble sequence is wrong, looking at redshift 0, that you need to take into account the fact that early type galaxies can be separated into fast and slow rotators. And possibly as you go to higher redshift, certainly as you go to higher redshift, this kind of schema doesn't really fit what we see. So we've seen this plot a lot today, looking at this compactification parameter versus the specific star formation rate. And the way that galaxies move around in this plot is thought to have to do with a number of very interesting things that might have morphological signatures. So major mergers, minor mergers, violent disk instabilities, clumps. And to actually directly find all those things is going to require more than putting things into Hubble types or doing Sirsic fits. So, you might go out and try to see if there's evidence for this pathway for the size growth of compact quiescent galaxies through dry minor mergers. This is a plot from one of Peter van Dokkum's papers indicating that the growth of the outer parts of these galaxies may be built up through mergers. Do we see direct evidence for this if we look carefully enough? I would say yes, if we look in the right places. So in one of the CANDELS fields, the UDS, there's a very massive, what I call a proto cluster at high redshift, so redshift 1.62. So this thing, doesn't quite meet the definition of a cluster present day, but if you evolve it forward to today, it'll be something like the Virgo cluster. And if you look at the galaxies, particularly the massive galaxies sitting in that cluster, you see a lot of merging. So I went and counted the close pairs, very close projected pairs in these protocluster galaxies and compared that to the field sample. And I find a galaxy merger rate that is much, much higher, 3, 5, possibly 10 times higher than that of the field. And many of these mergers look like this. They're little lumps, dry minor mergers coming in. So I would say yes. We are seeing in some places, perhaps in the densest environments, direct evidence for the buildup of the outer halos of compact galaxies through lots of dry minor merging. But I would argue that's not really the only path for these compact galaxies. So Greg Schneider will be talking on Friday afternoon, and if you're not around on Friday afternoon, I thought I would show a slide from that. So these are the same simulations we've been hearing a lot about, the HydroArt simulations. And in two of those simulations, you see something kind of interesting in that you can start off with something that looks a lot like a compact galaxy, not quite quiescent yet, at redshift 2. And over time, it appears to develop a star-forming disk. And I would say we don't quite understand yet, maybe somebody in the room understands yet, but what is triggering the growth of this disk, whether it was sitting there the whole time and just, something, a flyby boosted its star formation, or whether this gas was accreted later, either in sort of a cold mode accretion or through a minor merger. But I would say that things from this part of this diagram could possibly move back into this part of the diagram, and that we should think, not just assume that the structural evolution of galaxies is monotonic. Things are bouncing around in this plot. So if we want to go out and try to look for, minor mergers, major mergers, the non-parametric morphologies are a good way to do that. So this is an old plot now from my 2004 paper. GeneEM20 separates major mergers out quite nicely. It also does a pretty good job of defining galaxies along the traditional Hubble sequence. And in particular, I want you to notice this sort of upper corner here is where today's ellipticals and S0s lie. Mike mentioned these new and better ways of measuring particularly clumpy galaxies and mergers. So Peter Freeman developed these 3 new statistics, the MID statistics. And he did a test to see, doing a random forest training algorithm to try to see which of these parameters best match the visually classified disturbed galaxies in our CANDELS sample, and found that these 3 statistics actually beat GeneEM20 and CAS in terms of finding things that were mergers versus non-mergers, or finding things that were irregulars versus non-irregulars. So I think these statistics are really quite useful and are going to help us a lot with looking for weird galaxies in the early universe. So Mike talked about this work, trying to move beyond the Hubble sequence, and so putting these non-parametric statistics that can both capture the general bulge diskiness of a galaxy as well as its disturbance in a number of different ways. And so putting this into a principal component analysis and a hierarchical group finder, we come up with 7 unique groups. We're defining groups kind of based on this clustering algorithm, but you know, these are really a continuity of different morphologies. So if we look at, you know, how do these groups populate something that maybe you're a little more familiar with, like the GeNeM20 diagram. So this is this type 0, the compact galaxies that Mike was talking about. This is type 4, which are larger galaxies. You can see as we march through time, you know, these points for each type don't move around too much within this space, but we start to develop a lot of these, you know, these type 4 galaxies, which live in the space where today's large ellipticals are. And these don't really emerge in the GeNeM20 diagram until redshifts less than 2. By contrast, these things, the type 0, are galaxies that are small and basically smooth. We can't say too much about them. And so they're a mix of unresolved disks and compact galaxies. And as we know, these compact galaxies are really a dominant class of this redshift range between 1 to 3. So we can look at, you know, the quenching of these galaxies using a sort of classic UVJ diagram. And I can march through redshift space again for these. You can see at this highest redshift bin, 2.5 to 3, only the compact galaxies, this type 1, have any quenched galaxies, really. But as we march down in redshift space, somewhere around redshift 1.5 to 2, these type 4 galaxies begin to populate the quenched region of the UVJ diagram and really are dominating the quenched galaxy population for massive galaxies at redshifts 1 and below. What do the stellar mass distributions of these types look like? Again, there's not too many in the highest redshift bin. These type 0 are dominating the massive galaxies, particularly the quenched massive galaxies. So red here is the quenched fraction within that type. So we can march down again and see the emergence of these type 4 galaxies. And so, you know, by redshifts less than 1, these type 4 galaxies are dominating the massive galaxies, and particularly the quenched galaxies. So I've made a hokey SFR versus compactification diagram. I wouldn't take these specific star formation rates too seriously. They're computed from SED fitting, so they're not as good as other ways of computing the SSFR, but they'll give you a sense of how galaxies can move around in this diagram. So again, at high redshift, our type 0s are very much consistent with the compact galaxies that Guillermo has talked about. I want you to look and see how things are moving in these diagrams. So things that move that way, maybe evolving through size growth and perhaps through dry merging. Things that move this way are being quenched. And if we look at the emergence of these type 4 galaxies, you know, they're consistent with being drawn both from the mergers of these galaxies, the compact galaxies, but also the quenching of our more disk-like classes here. So what does this all mean? You know, we can look at a summary plot here. This is just fractions of types at a constant mass bin. So if we look and see how things evolve over time, again, most of these galaxies are falling into our compact class, which seems to be, you know, decreasing in importance for massive galaxies below redshift 1. And while these extended galaxies with the compact cores, the progenitors of today's early type galaxies, large early type galaxies, are increasing dramatically below redshift 1.5. These other, you know, more disk-like classes, you could add these all up and they would, you know, probably go like this. They're slowly declining over this time. And so I want you to note, though, that the emergence of these type 4 galaxies, the progenitors of the large early type galaxies, seems to appear before the rapid decline in the importance of the compact galaxies at this time. So this suggests to me that a lot of these disk galaxies at early times are partially what's feeding this population. Thanks. This is doing the same thing, only selecting instead of a constant mass, selecting at a constant number density. Here, this same trends are sort of more dramatic because you have more low mass galaxies at high redshift, more high mass. Your mass cut at low redshift is higher. These are clearly dominating the most massive bins at late times. So what does this mean for the evolutionary paths of high Z galaxies? Right, so this is our type 0 class. These are our type 4 classes. And we have these pictures that we've talked about for quite a while now. You start off with disk galaxies. Some of them have clumps, some are asymmetric, some are dusty. There's a mixture in here of the processes that we think of as violent disk instabilities and mergers. These can collapse and form into these compact galaxies. A lot of these objects are formed early on at redshifts greater than 1.5 to 2. These disks may also simply quench in a more slow fashion and end up as a disk galaxy. These compact galaxies can grow in size through dry mergers. Here's a nice dry merger I found in the CANDELS images. And both of these can end up as the types of galaxies we consider the large early type galaxies today. But I don't think that's the whole picture, and partly because if I look at this object and I look at that object, and I think back to the pictures from the hydro art simulations here, I don't think that schematic includes this possibility of the development of star-forming disks around compact cores. And so it's possible that these compact cores can evolve into this as well, and then go this way or then go that way. I don't know if this is really a separate path, or if really we should think about, there are some galaxies that go through these, whatever process is that forms a bulge. Some of them end up in our compact class, and some of these are really in a compact plus disk class. Maybe these are happening at different mass scales or different time scales. And then these objects evolve into what we see at late times as the large early type galaxies. So I'll just end with my summary again. We're really just getting started in analyzing the full set of CANDELS data. We definitely need to analyze the ACS images and get a better sense of what's going on at redshift less than 1 and see if we're consistent with the results from Cosmos and what Marcella was talking about today. But I think there's a lot of value in looking at the big picture, at trying to look not just at only compact galaxies or only large clumpy disks, but really putting the whole picture together and to see how these different classes or types of galaxies evolve over time and whether the number densities and the mass distributions and size distributions of those galaxies all hang together. So thanks very much.
All right, we have lots of time for questions. Yes.
Jenna, regarding the hydro art simulation showing the disk reform, is that image candlelight with noise added in there?
No, it's not. And if you add noise, you really don't see this disk until about here.
Right, that's what I wanted to ask you. I wanted to ask you whether it's just that it's seeing it too, the disk is there, you're not seeing it, or really it's not there.
You want to comment, Greg? On
I think it's clear, but
yeah.
it's much less bright than other times. It's really bright.
Marcella?
I have a lot of special comments on the classification for Pca usage, but I think I lost talking. I have a physics question. I'm intrigued by the initial results you showed about the merger rates being so high in the cluster rather than in the field.
Oh, yeah.
And I mean, we've been taught in kindergarten that the velocity in the clusters are high.
Yes, yes. I think this is I call it a Proto Cluster. So if you look at its, I'll go way back. If you look at its morphology, right, the distribution of those cluster galaxies, it's pretty lumpy. It's really a bunch of groups coming together. And so it looks like that.
So I wonder, I mean, obviously it's just something
Well, I think this is a very special time in the formation of clusters. It's when things are just coming together and they're not really virialized yet. So they're not moving past each other so quickly that they can't possibly merge. This analysis is based on looking at very, very close pairs. And you can go and look at the paper. So we do a bunch of corrections to versus the field versus not the field, corrections for projection effects within the cluster. And it's a very strong result. It's a very highly significant result. But this is one cluster. And so there are a number of clusters and protoclusters in this redshift range between 1 to 2 that Greg and I will be looking at the next year from the HST archive to see if this high merger rate is something that is consistently found.
But this is seen in MS-1050. I mean, D-Tran found this in MS-1054.
Yes.
And there she had spectrum too, which showed that there was a low relative velocity between the two members of the pair.
So how low is low? And
What
what
do
do
you mean
you
low? Did I say low? Or I mean low? I mean, it's MS-1054 that there's one.
Well, do the simulators, since we have been talking about simulators, do you see any such thing as simulations, or do you see that there's a structure and these are, would be fascinating anyway,
Mm-hmm.
but could that be such structure?
Yeah.
It's fascinating.
The other thing to note is that these two things are the most massive galaxies in this overdensity, but they're only 10 to the 11 in stellar mass. So if they turn into big BCGs, they have to grow dramatically. And the best way to do that is through lots and lots of merging. So it's plausible, but we need to look more. So.
This growth of a disk around a Copper galaxy is, I think, related to what Sandro was telling us
Yes.
a little ago, and is something we see very clearly in his cosmological simulations.
Yes.
Very nice.
Okay.
Any other questions, comments on this?
Maybe one last comment. So if we stack atomic galaxies, should we see the
I would argue that we're sort of selecting for disks we can't see by selecting things that are compact. If I go back all the way to my end here. I mean, you can put these, this is why I think the analysis that's being done at lower redshift by looking at the central mass density and how that correlates with things is so interesting, because my suspicion is that the central mass density of this is not that different from the central mass density of that. And then the question is, why do we see a disk around something like this and not like that? Are they, are these really different beasts? I mean, this thing gets counted as large and star forming, and this gets counted as small and not star forming. And it's, it's all because of that outer disk. So.
Will all depend on the later vision. Those giants with these, after the compression phase, will have to later vision back.
Sure.
And that could happen for at the given element. You have some guys that didn't have that level of vision. The gas vision is not completely constant at the same element.
But I don't see why we shouldn't be having the formation of upper action and actually know we start seeing it emerging from the mass structure of quench objects at the type of times. And how can these objects be if the universe is so dense? They're going to be very complicated and dense. So also from the data, already so Moro and we also with Cameron we start with the F9. These objects do not have the disk. They are really quenched.
Yeah.
And if later on some of them get some gas, God knows. There is also no problem in leaving them as they are and being these very dead things which we inherit from the stars.
Okay.
David?
We're not really taking advantage of the colors of these objects, the substructure of these colors at all in these types of analysis. And I presume that you chose as a rest frame something that's, say, middle or optical or something like
Right.
that. So you're mixing, say, the morphologies of the star forming or Pca versus that stars.
Mm-hmm.
Have you thought about some statistics which does some sort of a combination, separating those two and looking some cross correlations among properties as a more powerful way
Yes.
to get after the disks, which
Yeah.
are typically bluer, or at least a blue disk, or
Right.
interesting relative to the red disks?
Well, you know, this could be another chapter in Mike's thesis, right? So throwing in, you know, the morphology indicators of the same galaxy as measured in different bands and looking for dramatic changes, because that would show up different, you know, blue star forming disks around red bulges would pop up.
What we're talking about are in that language, and yet it's not reflected by this is the thing of being
Yeah.
taught by you or other people.
Yep.
Anyway.
Okay.
All right, at this point, we have time for a discussion.